Assalamu alaikum. Welcome to lecture 24 of data mining. Today we will continue with our discussion on outlier detection. We had introduced the idea of outlier detection in the last lecture, and we also did some basic categorization of outliers and outlier detection techniques. So today we will be discussing maybe a couple of techniques in slightly more detail. We talked about the distance-based outlier last time, which is a very simple outlier detection technique. We'll talk about the LOF today, local outlier factor, and we'll also talk about reconstruction-based outlier detection, which is based on the auto-encoder. And I think that would pretty much cover it all. Of course, the next topic that we are going to discuss is time series analysis. And we might start it today or we will start it in the next lecture. So today we also have a quiz, your last quiz, quiz 9 at around 1:30. So that's basically the plan for today. Any questions? So we were talking about outlier detection. And basically, if we talk about outliers, we said that there are outliers that are global, that are contextual, and one type of contextual is local outliers. And then we have what is known as collective outliers. So these are actually types of outliers. Local or contextual and global outliers are usually point outliers. They are single objects, while collective outliers are a group of points that as a whole are considered to be outliers. So these are the general categorization of outliers. In terms of techniques, the techniques could be, of course, statistical techniques, which are less popular in data mining. And then we have what is known as proximity-based. So proximity-based, as the name suggests, is based on the notion of similarity or dissimilarity. And within this category, there could be further subdivision according to how we define proximities. It could be distance-based or density-based or graph-based and so on. And then there is another categorization which is called clustering-based. So as the name suggests, clustering-based are techniques that uses standard clustering algorithms, and as part of those algorithms, they are also able to detect outliers. So we'll briefly discuss this today as well. And then the final one is reconstruction-based. So reconstruction-based techniques are, the idea is that you find a representation of the data, or you learn a representation of the data, and then you basically then reconstruct the original representation from the represented representation. And based on the deviation in the two, the reconstructed representation and the original representation, you can detect outliers. And the typical technique that is used in this category is the auto-encoder based. So we are going to talk about this today as well. So all of these techniques, by the way, are unsupervised techniques. There could be also supervised techniques for outlier detection. So, okay, let's get started then. So we had briefly talked about distance-based outlier last time. So just very briefly, so it requires two parameters, a parameter R, which is the radius of the neighborhood, and a parameter pi, which is the percentage of objects that lie beyond that neighborhood. And in very simple sense, or in very simple terms, an object O it would be an outlier if more than pi objects of the data set lie beyond the R radius or the R radius neighborhood around that object. So that's the simple definition. So this is distance-based outlier. So obviously this is a global approach to outlier detection. Both R uh, and pi are defined for the entire data set. The problem here is that many data sets may have different regions within that data set in which the density may vary significantly. And the notion of an object being an outlier might thus become different in different regions. So to illustrate this, maybe let me just. So let's say you have a dense region. This is a dense region. So you have lots of points here. Okay. So in this distance, if you have an object here, let's say you have an object here. Obviously, this object is quite far away from this dense region, because if you look at that dense region, within that dense region, two objects are very close together. So this object, when you compare it with those objects that are its neighbors, is much far away. So the relative, you can say the density of points around this plus, which is the object of consideration, is significantly different. So around plus, there is sparsity, and the neighbors of plus are in dense region. So in that case, this would be an outlier. On the other hand, and let's say if it's the same data set, this might be another region, bigger region, but it has very few points. And then we have another object plus here. Maybe absolute wise, this plus is as distant as this plus here, this one here. Absolute distance शायद same है circle से, इसका भी और उसका भी, ठीक है? इस case में, because now the distance from the region is same, but that region is dense. तो इसको तो हमने outlier कह दिया. But in this case, this may not be an outlier because its neighbors are also far away from each other. So in fact, in this case, you can think of कि आपका circle ही बड़ा हो गया और इस plus को include कर लिया. So there is no difference. While in the previous case, the circle, small circle had lots of points, and this point was just off that circle, but that distance is relatively far away as compared to the objects in its neighborhood. So this notion of a definition of outlier based on the density of objects in its neighborhood is another notion that we can use to find outliers, and this notion would give you would help you find local outliers, outliers that are defined by the context around them, or contextual outliers. So the technique that we're going to look into this, used to find local outliers is what is called a local outlier factor, which is also called LOF. So this is, as I said, can find local outliers as opposed to global outliers. The definition of an outlier is defined or described by the neighborhood around that particular point, rather than by the entire data set or some parameter defined over the entire data set. So, and this technique is quite similar to the DB scan algorithm that we studied while we were discussing clustering, because that was also density based. This is also density based. So let's look at this. So it takes K as a parameter. So K is the number of neighbors to consider. So the K number of neighbors to consider. So it's like the K nearest neighbor, and this is a parameter of the approach. So if you remember, when we discussed graph-based clustering, we also discussed a way of obtaining a graph from a similarity matrix by specifying K. So for each point, you find the K nearest neighbor, and you connect that point in the graph with those K nearest neighbors. So this is the same idea, and the K, of course, here is a parameter. The main advantage of using K as a measure of defining the neighborhood is that the neighborhood is just flexible. The K may be fixed. Let's say you take K is equal to 3. So that's fixed for the entire data set. But the neighborhood is flexible. If an object lies in a sparse region, then the neighborhood would expand to those 3 points in that sparse region, and the circle would be larger. And if an object is in a dense region, the neighborhood would be shorter because those points will be close to each other. You have a smaller radius around it. So that is one advantage of using K as a measure for defining the neighborhood. So from this, we define some other terms. So K distance. So let's say we are talking about a specific object O. So we are considering object O, and we are trying to find whether object O is an outlier or not. So the K distance of an object O, so this is basically the distance, basically the distance to the kth nearest neighbor of O. ठीक है? So let's say ये आपका point O है. So let's say these are the 3 points that are K is equal to 3. Let's say ले रहे हैं. तो okay, point अब miss हो गया. Let me draw it again. So K is equal to 3. Let's say ये O है 1, 2 और ये सबसे दूर है. तो मतलब आपका सर्कल ये बनेगा. And let's say if you consider another region और उसमें पॉइंट्स करीब हैं 1, 2 और 3, ये आपका सर्कल छोटा बना. ठीक है. So you find, let's say if K is 3, the first nearest neighbor, the second nearest neighbor, the third nearest neighbor. Your third nearest neighbor का distance है from this point is the K distance. Okay, which is also the radius of this region around O. So the radius is defined by K and is called the K distance. Okay. So this radius, the K distance would be different for different regions of the data set. For dense region, this K distance will be smaller. For sparse region, it will be larger. Okay. All right. So after this, we define the density around O, which is called the local. Oh, sorry. We define the local reachability density, but we do a smoothing on that. So local reachability. So this density is based on distance, and that distance is called the reachability distance. So let's define reachability distance. So reachability distance RD of an object O from an other object O prime. Okay? So O is the object of interest, O prime is any other object, is defined as max of the K distance of O and the actual D between O and O prime. So this is actually just meant for ensuring that the variability in distances is small, kind of a smoothing distance. So what is it doing? So we have an object O when an object O prime. ठीक है? O का कोई O का कोई K distance होगा defined by the K. Let's say K distance इसका ये है. O prime उससे बाहर है. So इसका K distance इसका radius है. O prime का distance ज़्यादा है, तो then this reachability distance would be equal to the actual distance between O prime and O. On the flip side, let's say if O का जो K distance है बड़ा है, let's say बड़ा radius है, और आपका O prime उसी के अंदर है. In this case, we do not take the actual distance between O prime and O, we take it as equal to the K distance, which is the radius of this neighborhood. So in other words, if O prime lies within the neighborhood of O, then the reachability distance is actually the neighborhood distance. Otherwise, it's the actual distance between the 2 points, जो भी maximum है. If O prime is outside the neighborhood, so it's the actual distance. So then this distance is actually used to compute density. So local reachability density of O there is another thing that we want to define. So we also define the neighborhood of O as NO. So this is the so this is a set of points in that neighborhood. Okay? And another thing that we need to consider is NO may be greater than or equal to K. Okay? Why is this so? The kth nearest neighbor, there might be multiple objects that are at the kth, that are the K distance from that object O. So of course, in general, it will be K, and maybe in one or few cases, it might be more than K, but generally, we take this as a separate parameter, the actual number of objects in this neighborhood. Okay. So N is the neighborhood around O. The actual number of objects in this neighborhood is the bar of this set, the absolute of this set. So now we are going to define LRD of O. So this is basically the summation operator, sum or the sigma. And this is for all the objects in the neighborhood of O, which is O prime in N O. Okay? And then we have so we have N O divided by डिनोमिनेटर में ये सम है, डिनोमिनेटर में ऑफ कोर्स रीचेबिलिटी डिस्टेंस ऑफ O prime from O. ठीक है, so this is the local reachability density of the point O. So what do we have here? Numerator में of course the neighborhood count for this object O, which would be around K or slightly greater than K. And then we divide it with the sum of the reachability distance of all those points in the neighborhood of O. So actually we want the distance from O to those neighborhood points. ठीक है? So which means that we will be looking at the K distance of O prime. If you look at the definition for definition for reachability distance, it's basically max of O. Now this would be max of O prime, and then the actual distance between O and O prime. Okay. So we are looking at the neighbors of O and the density around those neighbors. So just to take an example, let's say you have K is equal to 3, let's say, and you have an object O. ठीक है, न्यूमरेटर तो more or less 3 ही रहेगा, K ही रहेगा, right? डिनोमिनेटर में जो सम है 3 ऑब्जेक्ट्स का सम होगा, या जो भी इसमें नेबर्स में काउंट है, ठीक है. If those neighbors were in dense regions, those O primes, उनके इर्द गिर्द और ऑब्जेक्ट्स ज्यादा क्लोज थे, तो then this value would be larger. ठीक है. On the flip side, if वो sparser regions में थे, then this value would be smaller, because denominator बड़ा हो जाएगा. ठीक है. So this basically gives us a measure for determining the whether O is an outlier or not, which is what we call the LOF of O. This is basically the relative LRD of the neighbors with respect to the current object, of course averaged out. So उसको मैं लिख लेता हूँ पहले. This is equal to okay, so we have again the summation of O prime, which that are neighbors of O. ठीक है. And then we are writing the numerator actually. इस पे मैं यहाँ भी ब्रैकेट डाल देता हूँ. All right. So now we have the LRD of O prime divided by LRD of O. This is a ratio, relative densities का, and ये पूरा numerator में है. और नीचे of course, since we have n or k sums up there, we divide it, we take the average. So नीचे denominator में simply n O है. ठीक है. So average relative density of the neighbors around object O. So this is actually LOF. So उसके numerator में ratio है LRD O prime over LRD O. So if LRD O prime is greater than LRD O, then this value would be larger. Meaning that के ऑब्जेक्ट O के जो नेबर्स हैं वो उनके इर्द गिर्द डेंसिटी ज्यादा है, इसका मतलब है दे ऑब्जेक्ट O आउटलायर है. रिमेंबर जो मैंने डायग्राम बनाई थी, डेंस ऑब्जेक्ट के करीब एक ऑब्जेक्ट पड़ा हुआ है, वो डेंस है और ये ऑब्जेक्ट थोड़ा दूर है, तो दिस मोर लाइकली टू बी एन आउटलायर. If both of them are sparse, then that may not be an outlier. So this number basically thus quantifies the outlier factor for the object O. So the value of this number, of course, can range from 0 onwards, 0 to infinity in general. Okay? 1, or you can say less than 1 means that it's an inlier, meaning that it's not an outlier, it's part of a cluster. And greater than 1, it's an outlier. ठीक है, और जितना ज़्यादा बड़ा होगा 1 से, then it's more likely an outlier. And usually in practice you will have to you typically rank objects by LOF और फिर एक कट ऑफ लगा देते हैं कि इस कट ऑफ पे ऊपर जो ऑब्जेक्ट्स हैं सारे वो आउटलायर्स हैं और बाकी नहीं है. ठीक है. So essentially, this is the LOF approach for outlier detection. It is quite popular in practice. Of course, there are many variations of this as well in the literature, but of course, we are not going to discuss those. But the basic idea remains the same. So it's density-based. It uses the notion of the k nearest neighbors, and it's also a local outlier. It detects outliers by looking at the densities of regions of the local region. If an object lies, if its neighbors are in dense region, then it's likely to be an outlier. If its neighbors are as sparse as itself, then it's not likely an outlier. And also if its neighbors are as dense as itself, then it's not an outlier. So usually when an object is within a cluster, when its densities are the same, then LOF would be 1. Okay. ठीक है. So that was the second approach that we discussed from the proximity-based approaches. The first one was density-based outlier, which is uses a global notion of outliers, and then we talked about the LOF, which uses a local notion of outliers. So now, very briefly, let's talk about clustering-based approaches for outlier detection. So we have already studied many clustering algorithms, and some clustering algorithms, or almost all of them, can be used to find outliers, but some of them are more tuned for outlier detection than others. So what are the possibilities? So the possibilities could be, so the object, for example, is not part of a cluster. So then it's an outlier, obviously. So your algorithm, your clustering algorithm was not able to assign that object to a particular cluster. If that is the case, then that object will be an outlier. And or object belong to a very small cluster. So again, in this case also, the entire cluster might be considered an outlier. Actually, this is a case of a collective outlier, a group of objects that are outliers. So maybe after clustering, you have found many big clusters, let's say 10 big clusters, and there is just one small cluster with, let's say, a few points, 5 points, 6 points, 3 points, and the bigger clusters have hundreds of points. So then this small cluster can be considered to be an outlier. All the objects in that cluster can be considered an outlier. And also sometimes you can use object is significantly deviated from cluster. So of course, significantly deviated is a notion of similarity. So let's say your algorithm did find an object to be a part of a cluster, but you found that it is still very far away from the center of the cluster. Its standard deviation, for example, is very high if you are computing the distribution of all objects within a cluster and then finding the standard deviation. If your standard deviation is very high, or in the case of simple k-means clustering, if its distance from the center of the cluster is very high. In that case, you can call that object an outlier. Okay? So these are the three possibilities that you can have. By the way, this first option, so which clustering algorithm could give you a point that is not part of a cluster? So we did study one algorithm in particular. So for example, e.g., the DB scan algorithm. So in the DB scan algorithm, we defined three types of points: border point, core point, and outlier. Outlier was not part of a cluster. Okay. So in this case also, maybe usually k-means would typically give you clusters that are all relatively big. So this technique also, so it could be, let's say, a graph-based technique like C-whispers, or even DB scan, density-based clustering, and so on. While in this case, we have our, for example, k-means algorithm, where you use a distance measure to quantify how far away a particular object is from the center or the prototype of that cluster. If it is beyond a threshold, then you can call that an outlier. Okay. So clustering-based techniques usually are kind of more computationally expensive if your only goal is to find outliers. But if you're doing clustering as well, then this is a good, you can say, additional information that you can get from these clustering algorithms regarding whether an object is an outlier or not. But if you're focusing on just outlier, then maybe clustering the entire data set and then finding outliers might be computationally expensive. In that case, you just focus on outlier specific detection techniques, not based on clustering entirely. For example, you can use LOF, for example. So finally, let's talk about another technique which is more common recently: reconstruction-based outlier detection. So this technique has gained popularity in recent years. And it is based on neural networks, or the concept of auto-encoders. I will discuss that shortly. And the reason why this has become popular is, of course, because of the popularity of neural network, as well as the power of neural networks to model all types of data sets equally. So for example, when we talked about DB scan, so DB scan would typically work well for, you can say, numeric data set, or data set that can be described by metric similarity measures. So k-means, for example, would typically only work when you have numeric attributes only. But the reconstruction-based techniques based on a neural network can process mixed attribute types quite easily. You may have objects that are described by numeric attributes, by categorical attributes, nominal attributes, ordinal attributes, and so on. You can make a feature representation of all those attributes and feed into the neural network, and neural network will be able to process it uniformly. So first of all, let's talk about that representation issue. So how is that done? So let's say you have an object that described by, let's say, so let's just take an example. So let's say you have color as an attribute, then you have age as an attribute, you have income as an attribute, and let's say you have, yeah, I think that should be sufficient. Maybe you can also say rank as an attribute. Okay. So color is categorical and it has a fixed set of discrete values, let's say 3 values. And let's say you call them R, G, and B in your data set. But to use neural network, you'll have to properly encode it. So the best encoding for representing categorical attribute is what is known as the 1 of K encoding, or what is also known as the 1 hot encoding. Okay? So in this case, color would be represented by a vector of length 3 with just one value per representation. So for example, if you want to represent R, which is red, then you represent this as a vector of 1, 0, and 0. If you want to represent G, green, this will be 0, 1, and 0. And if you want to represent, let's say, B, this would be 0, 0, and 1. So of course, you now have 3 distinct values, but these distinct values have the relationship among them that only one of those values is 1, the others are 0. And that one value is indicating the value of this attribute, whether it's red, green, or blue. So then we have age. Age is numeric, so that was fine. You can use it directly as numeric. Then we have income, which is also numeric. That's also fine. And let's say lastly, you have rank. Rank, let's say you have, let's say we talk about in, let's say, freshman, sophomore, junior, and senior. Of course, this is rank, not just a set. There is a relationship between these values. So you can consider this to be as categorical, or you can convert this to numbers. Both are possible. In the case of neural network, you can convert it to number, maybe give 1 to freshman, 2 to sophomore, 3 and 4, or you can consider them to be categorical and define a vector of length 4 with 1 hot encoding. So let's say if you're done this, then each object is now represented by a vector. So let's say मेरे पास एक vector मैं बनाता हूँ 1, 0, 0, फिर let's say 25, and income let's say 10,000, 1, 2, 3, and then we have let's say I use integers to represent rank. So let's say 2. So सारे आपके जो objects हैं, they will be represented by a vector of this size. As such, they can be processed by the neural network. So fixed length vector बन गया आपका for the input for the object, and all of them are numbers. So numbers can be processed by a neural network. Okay, so now let's say the original representation. So let's say this is X. ठीक है? So this is the original representation, and this is also an input that will feed into the network. So the network that we have is a standard feed forward neural network. Okay? And in the simplest case, it will be a two-layer neural network. You have an input layer, you have a hidden layer, and then you have an output layer. We usually don't count the input layer as when we are counting the number of layers. We only count the hidden, the middle layer, the inside layer is called the hidden layer, and the output layer. So there's one hidden layer, one output layer. So this is a two-layer network. So this is the simplest case of a feed-forward neural network. And so input dimensions would, of course, be the dimensions for X. So let's say X, so there are M features for X. So we have input layer would have M inputs, one for each of those features that you have defined. Okay. So then you have hidden layer. So this would have a reduced number of features or representations. So this would be, let's say, I call this hidden H, which would be less than M. And then we have the output layer. Output layer would have exactly M outputs. So this neural network, in essence, is taking X as input and would like to repredict X as output. So that's why this is called auto-encoder. So it's encoding the input and trying to predict the input again as the output. Of course, it goes through some hidden layer of size H, which is less than M. So this is, again, this is supervised learning. Why? Because you have an input is X. So output is also known, which is also X. Desired output is X. Of course, the network itself would produce something else. There will be slight error in the output, but we know the desired output. We'll train the network so that it can learn this mapping from X to X while it goes through the hidden layer. Okay. So it is supervised learning, but we don't need any labels. Labels are already available from our data set. Okay. So self-supervision भी इसको कह सकते हैं. All right. So in general, in outlier analysis, we'll have a data set D, which have multiple objects. Okay. N objects. Okay. Each object is represented by M features. So you use this autoencoder, which has an input layer, hidden layer, and output layer, to learn the mapping from the input to the input again. During this mapping, the network would be trained, meaning that the parameters from the input to the hidden and input hidden to the output would be fixed. So typically we use backpropagation and stochastic gradient descent to train the neural network. So once the network has been trained on this data set, now whenever you give a new X, maybe from the same data set, let's say आपने कोई नई input X दी, उसकी कोई output वो predict कर देगा, which is X prime, I call it X prime, because exactly same जरूरी नहीं होगा. It's a predicted output. Both of them are of the same length. Okay. So of course, X prime is the reconstruction of X. So we fed in X, it went through some smaller number of layers, units, which is H, and then it was reconstructed back to X, which we call X prime. So, and we have learned this mapping from our data set. If for any given point, this difference between X and X prime is large, then it means that this is not a normal behavior in the data set, and it might be an outlier. Because a neural network has been trained on the data set, it will most likely capture the normal behavior in the data set. So in reconstruction-based techniques, essentially what we are computing is the norm between X minus X prime. So you can call it the Euclidean distance between X and X prime, for example, L2 norm. Remember, X is a vector. X prime is also a vector of the same length. You take the vector difference and take the length of that vector, or the Euclidean distance between these two vectors. That's the same thing. So if this value is greater than some user-specified threshold epsilon, then we say that this particular object, then X is an outlier. Of course, this epsilon has to be tuned or checked out first to find out which epsilon gives you the best set of outliers. So ideally, of course, if the network was a perfect reconstruction and this object was a normal behavior for the data set, then this difference between these two factors would be zero. The norm would also be zero. Okay? So they would not be, that object would not be called an outlier. But if this object was not a common behavior in this data set, then this difference would be larger. And when this difference becomes beyond a threshold which we specify, then we can call this a outlier. So this is the reconstruction-based approach to outlier detection. As I said, this has become quite popular in practice in recent years, and in the industry, it is commonly used nowadays. And one of the main reasons for that is it can represent objects that are mixed attribute types. Okay. By the way, this technique is not in your main textbook. जो हैंड की बुक है उसमें नहीं है ये. This is in Intro to DM book में. उस book में मिलेगी आपको. So it's not present in the book by hand. Data mining concepts and technique. All right. I think that is pretty much it for outlier detection. Okay, just a concluding comments on outlier detection. So we did not talk about collective outliers, although we did mention it briefly when we were discussing clustering-based techniques for outlier detection. If you find a cluster which is small, so that whole set of objects can be considered to be outliers. So that would be collective outliers. But there are techniques for collective outlier detection, but those techniques are very application specific. So for example, if your application is from the networks domain, computer networks domain, let's say you are trying to find specific types of intrusions, then those techniques would be tailored or designed accordingly. And this is actually a major challenge in outlier detection. So outlier detection is often application dependent. So a technique that is good for one application may not be found to be good for another application. Oftentimes you will have to tailor make a technique for detecting outliers in a specific application. For example, outliers for financial transactions, outlier for, let's say, telecom sector, outliers in the customer uh, retail business, for example. So all of those would have to be tailored to some extent to get good results. And one of the major issues is both those false alarms, so false positives as well as false negatives. So these would have different importances in different applications. So false negatives essentially means that you have not detected an outlier. Okay? So that would maybe a big issue. For example, let's say if you're talking about financial fraud, while false positive might be a bigger issue if you're talking about things like network intrusion detection. So maybe you're getting too many false alarms. So you'll often have to trade off between these two, and the trade-off would be decided by your specific application. um, we still have about 8 minutes. So next topic that we are going to start is time series analysis. So time series analysis is also not present in your two textbooks. I'm going to give you another chapter from another textbook from where we'll be discussing time series analysis. Time series analysis, as we will start discussing from more detail next time, is most of the techniques in time series analysis are very similar to the technique that we have already studied. What is important would be, as we will see, is to view that data set in a slightly different way and to shape your algorithms in the appropriate way. So let's say if you're doing classification, you will have to design your inputs properly. For example, if you're doing forecasting, again, that is prediction, regression, you have to design your inputs and outputs properly. If you're doing frequent pattern mining, again, you have to shape your data appropriately. The techniques, the end techniques would be similar to those that we have studied previously. Clustering example, outliers, and so on. So this will consume our next 2-3 lectures. And then probably we won't have much time to start something new. So that will probably bring us to the end of this semester. So I think I will probably stop here rather than starting time series today. Any questions? So you do have a quiz today, starting at around 1:35. So we still have about 10 minutes. So are there any questions? So this would be your last quiz. I'll be dropping 2 of your quizzes while compiling the final grade for the quizzes. So 2 low scores will be dropped. And any questions?